Embedded sensors can make objects aware of their situation in real-world settings, like industrial manufacturing, assembly, or construction. The most important aspect of being aware of a particular situation is being aware of the space wherein the object is located. We propose a solution that allows humans, as well as objects, to perceive space, aside from human visual perception, by employing sensors able to capture information about space, like the physical distance of co-located objects or their absolute or relative orientation. The idea is to make digital artifacts spatially aware of other such artifacts in their vicinity and let them reason about how close or far they are, or about their orientation and potential movement. Assume a person traversing a spatial scene with objects representing obstacles. Then a subtle, vibration-based notification system could let that person feel the distance to those obstacles, so as, for example, to be able to avoid collisions. An intuitive perception of distance here would be the intensity of vibration. The closer an obstacle is approached, the more intense the vibration. An intuitive perception of direction would be the localized vibration, oriented towards the obstacle. Combined, these two concepts give our vibrotactile space awareness solution. Defining spatially aware artifacts, we refer to the spatial outreach to which an artifact can interact with other artifacts as zone of influence. A zone of influence in a geometrical way describes the vicinity of an artifact, namely the subspace within which it can perceive the presence of another artifact or be perceived by others. Technological sensors for distance and orientation allow a spatially aware artifact to scan its vicinity for other artifacts. Based on the concept of zones of influence and the respective sensor technology, things can become aware of other things in their vicinity. We have developed an autonomous embedded spatial awareness solution based on the notion of zones of influence and technological sensors for distance and orientation. The implementation is based on our Pirit embedded computing platform, consisting of the Pirit stick-on computer, integrating sensor, actuator, and wireless communication capabilities, and the Pirit software framework, implementing principles of spontaneous interaction and autonomic peer behavior. The Pirit software framework facilitates interaction between mobile peers as soon as they have a certain spatial proximity to each other. A three-dimensional zone of influence is thereby defined for each peer, so that as soon as different peers come close to each other, that is, their zones of influence intersect in a geometrical sense, they can begin interaction. It is possible to define arbitrary three-dimensional shaped zones of influence. They are encoded in a special Zoe markup language and stored and carried with each peer as its profile. The possibility of spontaneous interaction based on zones of influence offers a broad field of application, ranging from applications in the automotive domain like drive-by-wire, to modeling and securing of danger zones in industrial manufacturing, collision prevention systems for moving peers like airplanes and supply carts, or even home automation systems like autonomic robots. Coming back to space awareness, we have developed a vibrotactile notification belt based on the notion of zones of influence and integrated sensors for direction and distance capturing. The notification belt comprises 8 vibra elements, circularly arranged all around the hip. A person wearing the notification belt can feel the space while passing through it. Approaching the Zoe of an object induces vibra notifications along the axis of orientation towards that object. Vibration intensity increases with the decreasing distance to the object. Simultaneous notifications occur whenever more than one Zoe is approached. Vibra notification becomes sustained as the Zoe and the respective object are approached more closely. In particular, the vibrotactile system is implemented based on an AVR Mega32 microcontroller, wirelessly interconnected with the host computer by using a ConnectBlue industrial Bluetooth serial port adapter. The 8 tactor elements, basically cell phone vibramotors, are controlled by a Darlington transistor array. Vibration elements are independently controlled by microcontrollers' analog digital ports. Vibration intensity is controlled by a pulse width modulation. In the demonstration here, position and orientation of the belt, or the person wearing it, is tracked with a lab-installed, highly precise ultrasonic tracking system. Assuming objects to represent obstacles or points of risk or danger, the VibraBelt solution has high potential for advanced worker safety equipment. Whenever eyes and hands are in charge and human attention is tied to the primary task, space awareness of approaching zones of danger are better notified via modalities other than vision and audio. Tactile notification appears underemployed in pervasive and ubiquitous computing interface design. Their properties of delivering notifications or alerts straight to the body in a very subtle way, however, make tactile systems a promising candidate to improve on the perception of space.